In this video, we will discuss about the refraction at a convex spherical surface. Suppose we have a spherical surface like this, and let's draw a principal axis. See, let this region be some denser medium. Let this side be denser and this side be rarer. Okay, and let the refractive index of the rarer medium be mu1 and the refractive index of the denser medium be mu2. Let's place an object O in the rarer medium. Here we are discussing about the refraction happening when an object is placed in the rarer medium. And the light ray from the object go like this, and at this point it will undergo refraction. Before that, I have to draw a normal. For a spherical surface, normal always goes through the center of curvature of the surface. Let this be the normal, and that normal is going through the center of curvature of the spherical surface. So when a light ray travels from the rarer to denser medium, it bends towards the normal, and we get an image I in here. So this is the ray diagram. So we need to mark the different angles. First, the angle of incidence. The angle between the incident ray and the normal is called the angle of incidence. So I can mark I in here. And the angle between this is the refracted ray. This is the refracted ray. So the angle between the refracted ray and the normal is called the angle of refraction. Let's call that as R. Now let's mark these two angles as some alpha, some beta, gamma. Instead of gamma, let me write phi, because we'll get confused with R and gamma. Okay, so let's take phi in here. Now let me mark the points. Let O, this point be some P, and let's drop a perpendicular from this point. Let's call this point as A. From A to the principal axis, let's drop a perpendicular, and that point B, let's say M. This is 90. Okay. Now, okay, so we have the representation. Now let me consider the triangle OMA. Before that, applying Snell's law at the point A, we know Snell's law is sin I by sin R is equal to a constant. That constant is the refractive index. Now the ray is moving from the rarer to denser medium, that is from medium 1 to medium 2. We can say refractive index of the second medium with respect to first medium, or that will be equal to mu2 divided by mu1. Now since these angles I and R are very small, see the refraction is almost like this. Okay, which means this height is very small, that is this AM is approximately, or AM is very small, so that this angle I and R are very small. So I can write sin I approximately equal to I, since I is very small. For small angles, we have for small angles we know sin theta is approximately equal to theta. Similarly, sin R is approximately R, since R is also very small. Now I can rewrite this equation. Instead of sin I can put I by sin R is R itself. I by R equal to mu2 by mu1. which will give, cross multiplying, you will get mu1 I is equal to mu2 R. Let's put this as equation number 1. Okay. Now let me consider the triangle. Now let's first consider the triangle OMA. Consider triangle OMA. We know this alpha, see, this is our triangle AOC. I'm actually considering the right triangle OMA. Before that, let's look at the different angles. See, this angle is I, this angle is alpha, right? And this angle is beta. And we know the exterior, see, I is the exterior angle to alpha and beta. So I can write I is equal to alpha plus beta. That is according to the property of the triangle. Exterior angle equal to sum of the other two interior angles. Similarly, when I consider this triangle, that is this AIC, this is AIC, this angle is actually beta, this one is R and this one is phi. So here the exterior angle is beta. So I can write beta is equal to sum of the other two interior angles, R plus phi, or R equal to, we need I and R. So I is this one and R will be beta minus phi. Okay. So the equation 1 will become mu1 into, instead of I can write alpha plus beta equal to mu2 into, instead of R I can put beta minus phi. Okay, let's call this as equation number 2. Now let me consider the triangle as we now back to the triangle OMA. Now consider triangle OMA. When you look at alpha, since alpha is very small, I can write alpha approximately equal to tan alpha. For small angles, we know alpha is equal to sin alpha is equal to tan alpha. Alpha, when alpha is very small, approximately, okay, not exactly. Okay, when alpha is small. Okay, so tan alpha is equal to tan alpha. Tan alpha is equal to opposite side AM divided by adjacent OM. So alpha is equal to AM divided by, see one more thing, this P and M are very close to each other. So OM is approximately equal to OP since PM is almost 0. So instead of OM, I can write OP. So this is the value of alpha. Similarly, beta will be, beta is also approximately equal to tan beta. Now we know tan of angle will be opposite side AM divided by adjacent side MC. Okay, so therefore beta is equal to AM divided by, instead of MC I can write PC. As we said before, this PM is almost equal to 0. So PC will be equal to MC. Okay, that's our beta. Similarly, now let's consider this triangle AMI. Consider triangle AMI. We have phi is equal to phi is equal to approximately equal to tan phi, because phi being also small, which is equal to tan phi is equal to opposite side am divided by adjacent side. Adjacent side here it is mi. Okay, so phi will be am divided by, instead of mi, I can write pi. So we got alpha, beta and phi. Now let me put all these values. I circled all these values in the equation number 2. So we get, so this equation 2 will become, substituting in 2, we have mu1 into, instead of alpha I can write am divided by op, plus instead of beta I can put am divided by pc is equal to m2 into beta is am divided by pc minus phi is am divided by pi. Clear? Now we can simplify this equation. Here am is common in both sides, so that can be taken out. mu1 into am times 1 by op plus 1 by pc equal to mu2 into am, again here also am is common, 1 by pc minus 1 by pi. Clear? This is the mu1 from here. So you can cancel this. So now let me put the values of v, u and r in here. U actually means the distance of the object from the point P, or the pole of the spherical surface. So this is the u, and this is u actually, and from P to the image we'll take that distance as v, the image distance, and we got one more factor, that is the distance between P and C, that's our radius of curvature r. Okay, so one more point, whatever be on the left of P, we have to take that as negative, and on the right of P we have to take that as positive. So this equation will become mu1 into 1 by, see OP is actually u, that too on the left of P, so I have to put minus u. This is u, okay, plus 1 by PC, PC is actually r, that will be positive r since it is on the right hand side. So mu2 into 1 by PC, PC is again r, minus 1 by pi is actually v. Okay, now simplifying this, you will get mu1 minus mu1 by u plus mu1 by r is equal to mu2 by r minus mu2 by v. Now rearranging this equation, you will get, bring this v to the left so that this minus will be converted into plus, so that mu2 by v minus mu1 by u is equal to mu2 by r minus mu1 by r. So this equation will become mu2 by v minus mu1 by u is equal to, this r is common, so that I can write mu2 minus mu1 whole divided by r. So this is the expression for the relation between the image distance, object distance and the radius of curvature for a convex spherical surface. Clear? Now what happens if the first medium is air? If the rarer medium is air, if the rarer medium is air, then the value of mu1, refractive index, absolute refractive index of air will be 1. So the equation will become mu2, or in this case if it is air, we have mu1 equal to 1 and mu2, let's say it as mu. So mu by v minus 1 by u is equal to mu minus 1 by r. Clear? So this will be the equation. See, this is actually mu and this one is u. My mu and u always look the same. Okay.